So today, I'm gonna introduce some Gapless. What is Gapless mean? Good example, Gapless. So today one. So my lecture was I'm too busy, so my lecture is full of like a typo and mess. I don't have time to clean up at this moment. So, but anyway, so I don't know. There are only three lectures left. I don't know how much I can clean up my lecture notes in coming 2 weeks or something like that. Yes. And then I didn't post the last homework, which will be done tonight. So anyway, so sorry about that. So almost like too much today. Today's plan is to show so-called transformation. And then first, second, assumption. Saying that is the strictly half integer. Whatever. Like a strictly half integer, then so the particle in chain. Number 3 is introduced by AKLT. So that's the plan of this today's lecture. So to get usefully some part in chain, we consider the point Hamiltonian. Oh, sure. So when JC is equal to J, it's nothing but Hamiltonian chain. Want to diagonalize this Hamiltonian? 이거 쪼다보기는 transformation. diagonal. That's the important part. So what are Joe here? We have transformation. So introduce. So this one is the introduce harmonic operator. And then and the approximate. So this C operator. So suppose you have the P system. So this way, plus can be understood 0, 1, 0, 0, which is same as plus. Yes, minus f, which is and S3, so S3 can be understood like this, which can be understood as the like this thing. And then this can be understood as the entire f minus 1 half. Can you see that? If y is equal to this one, can you see that? The point of it. Sorry, I think it's a bit confusing. So if you apply this one, you should get the minus 1 half of this one. And then if you apply S minus 1 half, so this S analysis being done, so you just get 1 half like this. On the other hand, if you apply the plus up in, so this will see acts on the an identity, so then we get on the top. So this is what exactly what. Okay. So now this single thing operator can be constructed from F and F dot. However, so this operator must be L side. So we have an L side like this way. So there is some position here. So you cannot simply use this method to construct this Hamiltonian by F and F dot. What you need to do is the following. So to introduce the so operators, J just give you very ad hoc, but J is J minus 1 half plus J is equal to then S minus J is J e to minus 1 half over L. So this N is a numbering operator. At side L. On the side L. So this is the number of 0, and this is 1. That's okay. So then we will see the check first thing the check computation relation. So first thing what we need to do is the construct this operator whether they just satisfy the correct correct computation relation. So to do that, first let's consider the this one E I and J. Okay. So if you consider that so if Nj is equal to 1, okay, so this term so Nj equal to 1, this term is minus 1, right? This term is minus 1. So therefore it becomes minus Fj. And J is equal to yeah, minus 1. Sorry, and J equal to 0 is just yeah. Yeah, and J equal to 0, if J equal another if J is another type. So therefore it becomes just minus Fj, the same as it, the minus Fj. You understand? Here, e to pi I Fj, f is minus Fj, e up. On the other hand, here is the just an Fj, which is equal to 0, but this is equal to Fj. Okay. So therefore, this is minus Fj. Okay. How about this one? So this one, if you act on e to the pi I, then fj. If j acts on this one, you will get the negative sign. And which is you get a 0. So it's just 1. And j equals to 0. So if fj acts on the spin up, you get the spin down. And if you act on pi I and j acts on the, this is 0. Okay? So therefore this is 1. And this which is equal to fj spin up. Okay? The same thing happening here. Fj e to the pi I and j. And which is 0, which is the same as Fj. So therefore this is Fj. Okay? This is equal to, so this is equal to 0. Okay, so they are equal. The similar way, so one can show that it's a good exercise to do by yourself. Based on the moment. So therefore, so and also so they so So if the e to the I sum over L so e to the I and I and L and then Fi, Fj or dagger. Then anti-commute if J is not equal to L. So that's very easy. I mean, they just commute. They just commute. So therefore, if you just consider the case, I think I'm doing something good. So you can check out the E to the sum over and L. This is anti-commute. Because of this guy. Because of this. When J, L is equal to, sorry, L is less than J. Okay, so that's what we're going. Furthermore, so one can show that the E to the I, sum over L, J, and J in L together is anti-commute is equal to 0 over L is greater than J. Okay, so sorry, so this implies, so this anti-completion implies this guy, and this implies this. Okay, so when that ends up here, this guy, implies this. Okay, so now if you use the this relation and then see the computation, so let's try to look at the computation relation. Sj plus minus Sk plus minus, and the computation relation is equal to when j greater than k. So here you need to be careful at J dagger E to the I phi. So I define the E to the I phi J is sum E to the I phi sum over L less than J and L. So these are E to the I phi J. Okay, so then this is E to the I by J, and the Fj dagger, and then the K dagger, E to the I by K. So when J is less than K, E to the phi J commute with the both this guy and this guy. So both this guy and this guy. So therefore, so you can remove as you can treat it as a scale. Yeah. Scalar quantity so that you can put it outside. Okay. So that's the case. And then so this is proportional to so this Fj dagger and then this guy anti-commute. So this anti-commute, and also these two will anti-commute. So Fj Sk anti-commute is equal to 0. Okay? And also Fj, and here, as we saw, E to the I by k is anti-commute. Okay? So therefore, this should be equal to 0. So therefore, you can show the commute as we expect. Okay. And then the other thing is the same as before. So if fjk v and sk v can be shown that they anti-commute. So using the fact they anti-commute when j is not equal to k. Using that one, so you can show this is also equal to 0. And when j equal to k is exactly the same computation as here. So therefore, we can just use this one. So now, to write down, I don't know why they erase this word. Unfortunately, I need to wait till the blackboard will be done. So now also the Hamiltonian is something like minus j over 2 gamma over j. Okay, and then plus and then minus jc. Hamiltonian is given like this. And then, so we will realize that this is c j plus 1, sorry, is plus and it's minus j. If you use this transformation over there, this can be written as the j of over and j plus 1 other. Like this. Okay. And then we know, so here we just have a difference is plus 1, right? So this is, if you have plus 1, this becomes plus 1. And they cancel each other most of the time. And what's left is different. And we already knew that the e to the pi I and j, fj is just fj. So therefore this is equal to sum over just 1 other and then fj. Okay. And then you can do the Harmonic conjugate too. The same thing you can do. And then you can take a look at this term too. And this can be understood as it's just a numbering operator. Like this. So it just only spin up and down. So spin component, spin variable just spin up and down. For example, if this is the spin down n equal to 0, so therefore you get a minus 1 half. Spin up, you get a 1. Therefore you have a plus 1 half. And you can do have the same thing. Okay. Oh, sorry, maybe different. I mean, they commute, so the ordering doesn't matter. So therefore, this Hamiltonian can be written as follows. Okay. And I just dropped the constant term. So I just dropped plus some constant, which is not important. I just dropped constant. Okay. Okay, so you just do that after that you apply Fourier transformation. To get the diagonalized form. Fourier transformation. So the Fourier transformation we can do is as follows. Fj can be understood as correction and S is the number of sides. Sorry. So now sorry, not X. So you have pin chain, so you have a number of sides. Is S and sum of them. Okay, and this is the length listed A. So each has to separate one. Okay. Okay. So then what we have is that the so now so we know the Nj is just a numbering operator. So this is just a J Fj. Okay. Okay, so therefore sum over Sj is equal to sum over J Fj, Fj, and then you just plug that one into here. Plug that one into here, what you get is a column. Sum over Sk, Sk prime, and then sum over E to by K minus K prime Rj. J and then K and K prime. Okay. And now, so if you use this just already Fourier transformation, this is just equal to this guy is just equal to Ns times delta K prime. The Fourier transformation. Therefore, this will give you sum over Sk touch Sk. So I just treat this. How about the character? Unfortunately, everything works. I think what I need to do is erase. Okay. Do the same thing. So sum over Fj plus 1 target Fj. So this one can be understood as if you use that rule, so E minus I K A Sk target Sk. I mean, okay, Sk prime. I mean, And it's the same thing. So I think you just equal to 1 over S, and the sum of the symptoms of your E to E, I, K, or J, like this. Because I mean, here just shift by +1, you just put it here. Okay. Oh, sorry, maybe minus. I'm not careful about sign together. Yeah, actually, it's a minus on it. And then, yeah. Okay. And this one is again equal to NS delta KK prime. So this means that this is equal to E to the minus. Like this way. So therefore, you have minus J over 2 sum over J, Fj plus 1 minus Fj plus coefficient conjugate is equal to like this. Okay. So how about last time? Last time, you can do the following. So last term is sum over J and J, and J plus 1. Okay. And this term is the sum over half Ij, Bi minus J, and I and J, where Bij minus J is equal to minus Jc over 2 or 0 when I is equal to J plus 1. I minus J plus minus 1. And we know the BQ is equal to sum over R, dr, and E to I, Q, R. Okay? And so therefore, it is equal to, so B1, E minus I, Q, A, plus B minus 1, E to I, Q, A. And we know that the B1 and B minus 1 is equal to this guy. Therefore, this one is equal to minus JB plus QA. Okay. Okay. So then if you move to the Fourier transformation, if you do the Fourier transformation, this one is equal to, so 1 over 2 and S. Okay. And you plug this one into here, you get out. You get out. So therefore, at the end of the day, the total Hamiltonian will get is as follows. So if you plug them together, and if they plug them together, H is equal to sum over omega k sk dagger sk. So what we have is the N is equal to this one, And then this guy is equal to this one. So now for omega k is equal to JC minus J of KF. And then there's a term, interaction term. So K prime and K prime. K prime, so therefore, QF so that's a conclusion after Fourier transformation. And this can be treated as H interaction term, as we saw before, H interaction. And this is the negative term, can be understood as H. But, well, okay. Any questions before? Okay, so both sides is very big and NS is very big, so that you can ignore interaction term. Then you can just take a look at it. And then the ground state is the so when JZ is equal to J, so this is the Heisenberg ferromagnetic case. In this case, and we just assume the NS is greater than infinity. So then you ignore this time the ground state energy H0. Ground state energy. So the spectrum is omega k, which is 2J. Like this. So this is the energy spectrum. So the energy spectrum looks like this way. So okay, so now it becomes something like this. Okay. On n over n minus pi over a in ground state. Am I doing something stupid? Something wrong. Sorry. Sorry, is it true? Is it okay? Is it okay? Something like that. So the ground state is here. And then, so there's a continuous spectrum you can have. And of course, ground state is something like this one. So this is a ground state. Okay, but to make it excited state does not cause any like so this is the second derivative 0. So this point is second derivative 0. Okay, so therefore, in fact, if you try to rotate so everything by the state, like spin down, and then E to D, so try to rotate as that. So this one, you can just have like something like this one. And then plus zeta over 2 sum over with plus J 0. So now we follow it, so it just and the order. So if you try to rotate all the sides by in x x coordinate, try to rotate infinitesimally by scalar, all the sides by infinitesimally. So you can just act as 0. So you remember that Sx is equal to S plus S minus divided by 1 half. But the S minus that analyzes all the things. So therefore it's only S plus movement more like. And this one, so as you recall this as plus of J and sum over J, all J is equal to sum over Fj squared and E to the other by J. So like this. Okay. And by J as this one is the so just 0. So because it's just all spin down state. So now what's left is S plus J. And this one is equal to plus I theta over 2 sum over E. So if you do that, sum over Fwj. So if you do this transformation, you just get the current and separate K to T. The last one. If you do the switch transformation, you do that. So this means that the so this means that no cost energy to rotate that spin, all the spins, all sides simultaneously. So then, if you have a spin down state and simultaneously rotate like this way, whatever, around the x-axis, if you try to rotate the x-axis, it doesn't cause any damage. So this is going more. So the original Hamiltonian is the rotational invariant in terms of x and y and z. But once you set the ground state as a spin down, it breaks the such symmetry. You do this state clearly only just enjoy this z-axis rotation, not x and y. But if you act at the x and y rotation, you get a different state without cause any energy. Any questions at all? Is it okay? So what we did is that it's very nice. So the original horizon is now diagonalized like this way. So what we did is just use the Fermat operator to construct the S spin operator, spin variable, and then after that you just do the Fourier transformation. That's what you do. Then we can just diagonalize the problem. So now let's look at that JP equals to 0. So this is called X1 thermodynamic. Of course, the system is really gapless. To make it excited state, you don't, it doesn't go to energy. There is no gap to the first excited state. So in this case, so the omega k is equal to omega k looks like this. So this is pi over a. This is pi over a. From outside the missing. So now to make the Hamiltonian, the most ground state, to make it the ground state, you only have this quantity, all the quantity is negative. Negative. So therefore, the k can just take the only like this state. So this Sk is the fermionic operator that creates a fermion with moment of k. And that can just fill only like this part for ground state. So since it's negative, so if you just need to fill up, it becomes the H becomes lowest. Is it okay? H becomes lowest. So that's four. So this is pi over 2a minus pi over 2a. This is pi over 2a. So this is in fact become Fermi surface. This and then this is Fermi momentum. So this part is Fermi momentum. And to make the system excited, you just add some state into here. You just need to create state around here that will create the excited state. So it brings this one into here and so on. It will create that excited. So there's really infinitesimal moment. So the length is really 1 over a. Is 1 over a is the in moment. So you can just so the system gapless. So so this part is called the half field state. Half field margin. The state is grounded. The half field means the only thing the negative part is filled, but the for positive side is not filled. Okay. And the energy can be estimated as follows: sum of total microphone task, sum over k, which is less than 5 over p, and like this one, times j. So this is the count of this x line. Is that okay? Any question at this moment? So the system is again. So here is also Gapless. I will reverse. So this is the Gapless. Heisenberg ferromagnetic. This is also Gapless. Universally formed. In our dimension, so you can see this if you use the Jordan-Wheeler transformation, ferromagnetic is the really Gapless. But for anti-ferromagnetic, Heisenberg transformation in model. So this also is the unique ground state and gap. And then, sorry, when f is equal to 1/2, strictly. So the 1/2 case, as I mentioned, is the gamma case in 1931. I mean, I can. If you try to, yeah. So if I try to explain this method, it just takes like one lecture for all explanation. So I'm gonna do that. I'm not gonna do that. Instead, I will introduce so-called LSM. Sure. So that's the statement of the LSM. I mean, basic explicitly show it's a gapless by just solving energy spectrum. But here is LSM is 1961. It's a much more general case, which I'm going to prove. So the idea is that the so there's a so ground state, and you apply some operator, which neutral operator, I call it as LSM. You get the state LSM. The idea of loop is the idea. So then, so we would like to show this with phi. So this ULSM is something non-local operator. Or the operator that rotates and we're still the J. So we create such a state. So this means that if you have a site inside, like this way, so ground state is supposed like this way, or whatever state is like this way, and then this operator is just trying to rotate the east side direction by in the axis of z but changing the rotational angle side by side. You understand? So if you increase J, the angle will increase by 2 pi over n. So you just increase the rotational angle as you move around the spin chain. And at the end of the day, if you come back to here, when J is equal to S, you get a 2 pi. So therefore, the rotation will cancel if you come back. That's the operator, and we would like to first show that this state is infinitesimally bigger energy spectrum than ground state. So what we're going to show is as follows. So we are going to show the phi LSN state with Hamiltonian of Heisenberg is equal to minus ground state is less than like this. We're going to show like this one. Where so now this goes to 0 when ns goes to infinity. Now this is the LSM with the infinitesimal how is it? Higher energy than the than grounded energy. Okay. So the Hamiltonian then assuming H is equal to J sum of S R S okay SJ like this. Okay, so then if you use the configuration I say here S X so SJT SJ minus like this way, you have the configuration. What you get is that the E to the minus always stay here SJ plus minus. That you can show by using the configuration. Is this correct? Wait a minute. No.
SC equals to S plus S minus. Yeah.
Sorry, I think something is strange. So, you think? So this is the case, right? Sorry. Yeah. So distributed. Okay. So if you use this computation, you can show this one. So the outcome, Hamiltonian we have is that the what we do. By using this relation, so we define that sum is like this way. But output, if you look at the each side, so each side you have a rotation theta j plus 1 and so on. So the difference you are here. So the output, and then so if you take the difference, like this one, with delta j. Oh, sorry, delta theta is equal to 3 pi over n. So if you just take a difference between original Hamiltonian, so this will cancel, and then I define this one as minus delta j, and this is minus delta j, and then the difference is like this. So now if you change this way, is this half over j, everything. Okay. So this means that the sum over j, everything. Similarly, you can do the same computation, or you take the different computation. Okay, so you understand Hamiltonian, you understand Stagger minus Hamiltonian. You just take a conjugate of this. Conjugate means that so you just take the phase difference. is equal to 1/2 over J, and then E is I, the outsider, minus 1. Yeah. Okay. So now we just evaluate this L7 state, Hamiltonian L7 minus H E minus G is equal to ground state given L7 stagger Hamiltonian given L7 minus H and the ground state. Okay. And we already evaluated this. But to make it a bit more transparent, so you just add so this one, and then so this one is less than if you add it's a unitary, so you LSM H you double LSM minus H and if you add this term, the right hand side should be bigger. Or at most of zero. If it is a zero. And then so you just sum them up. So theta I plus theta I. What's going to happen is that this one is equal to so the reason why we add them together is we have a common factor, both the outsider minus 1. Okay. And we know that the difference. So this one is so this one is less than. Sorry, I'm confused. So I thought this would be before. There's some mistake. Sorry. This is less than 2 times 1 minus cos delta theta. Like this. I just got confused. Why? Let's see. Why is that? Can anybody drive this one? Um, sorry. Let's try. So S plus J is X, J plus I is Y, J. Is it correct?
Yes.
And the plus minus is like this, right? Okay.
变形。
Sorry. I don't know. So it's plus J is minus J plus 1 is this J is J plus 1 S. Plus cross term. Like this. And then Y. Sorry, this part I. Oh, sorry, it's written in the. Sorry. So this one. Okay, so sorry. Sorry, this step I don't know. Let me check. Okay, I will derive this step after the break. And if you assume this one, so this one is equal to less than is equal to delta theta squared and 2s squared L, which is equal to 85 squared S divided by L. Okay, where I used the function here, I used the cos x is greater than log minus x squared divided by 2. And also, we use the ground state as J is J plus 1 ground state with the norm of S and then less than S. That's why we use. Okay. So this is the way of showing that the not L. So L and F. Sorry, my notation is F here. That's all side. And this is goes to 0 when S goes to 0. So therefore, so this state is really infinitesimal higher energy than ground state. That's right. And to conclude the proof, well, we need to show that this LSM and ground state is the orthogonal. It's not the So this one we can use translation environment to show this one. But before showing this one, let's take a 10 or 15 minutes break to derive this one. To derive this. Okay, let's take a break.
那里面是有些它是，就是每过一个节点赚多少钱，然后你缺多少个人。哦。这个是个怎么办？说什么呀？我真看不，你这个我都不知道在哪个机位。我看哪个同意了？但是这个就是对，这个东西他就把它命名成为什么？它是也看就很还有看这个还有是这么长。对，都是看这个假如他就是大概这个样子，不知道他会啥。然后还有一个因为就是你的话有一张英文的脸，对，这样子就行啊，就是那个哦，就是这个其实跟对面挺像的，因为这个像跟他一样，就是现在不是位置，然后交换，对，他这是他的意义，为啥？系统。因为单点里面就整个链和背后的，对关系不一样，不能让对你说那个不能好，对关对关设备Why is this term always possible? 所以就像这就点系统化，哦，我想买个新的，原来是这样买的，这个这不比老菜买的好。算 and also this one is from the这次是因为对于一个基态能量都是最低的，然后这个东西是基态，这个东西是一个基态，所以它比它大，这厉害。哦，再放一层。哦，这样子。那个放一层就是这个 H 的底下不是那个还真是，确实这样。我是觉得，马上看。
Oh, I see. That's true. It's not the correction.
因为这个是他们，这儿开个飞机，但这样并不是他的，会看咱这个公司哦，这就是当你这样的你就是这个说那个一阶型，就说一个是一个派的，一个指标到底过来，这个算是怎么算的？就说一个上升指标到底跟一个派这种这个 几个确有几个，我看自己得到的量级。你是超级这个我在旁边一样，这个学习，这几个是太像你公司或者二高，他是在他都会看过。跟电源，我觉得就是哪里强，就是哪里强的。对，这该领的，这现在不是没到我的。我是别人的，我当时别人也在说的，这是一些说的地方在，放在一个前面的潜力，双子合作，我有点奇怪。这个数学是可以用得上的。因为我有两个，因为我看这种英文注意力不太，所以这方面要注意。我觉得这个有个那上那个 S 说这个换对一个，你可以问问题。六，你是每个朋友的，这个都不要。它上面这么写的上，这个 S， 它是但是对那个类比来说，它是这个算法是反对的，所以为了解决这个困难，我才给它讲成这样子一个项目。因为这个 S 和本身是对的，然后如果那个如对比层我就反对一些，对，然后他们计算都是不能。对，但它确实以后后面计算的时候就没问题了。这个。说到没想出我应该很多写跟着算，应该都还好。说 AKLT 这个话分两个呀，就凡是属于能力的话。这个鸡脖，它什么都没。高度的平均相对导致那个。对。
Yeah. So I think after people come up, yeah, we need to, so I will post homework today, and which is due in 2 weeks or something. Yeah. And then after I will have a last lecture, and the week after it's going to be final exam. And then final exam, I don't know whether my at least 120 people register my course. I'm not sure. Undergrad and graduate may like a different group. I don't know. Somehow maybe something may have okay. And I need to talk about final exam too. Okay, so shall we resume? So this one step is actually very easy. And I missed this I missed this one. So in fact, what's really happening is that the S plus J, S minus J plus 1 plus S is minus J, S J plus 1 plus is equal to 2 times Sxj, Sj plus 1x plus Syj and Sj plus 1. Okay, that's the case. And now this can be negative, but I mean this is actually negative. So this one is the negative quantity. So cos theta, cos delta theta minus 1 is negative quantity. Okay. So therefore, so I just take absolute value. So this is equal to just the absolute value of cos theta minus 1. Cos delta theta. Okay. And then 2 times this one is just exactly this one. And if you take both absolute value, you just have the inequality. That's it. That's it. And then if you use this identity, you get this. So that's energy gap between LSM state and ground state energy. Nothing. Now, okay. Okay. So now we want to show this one. The last time we stated that the alternative ground state. The key step is that so we will show a column. So key step is to show this one. So so this means that when x is half integer, then there are some. Okay. So this means that the LSM state is different from ground state. And to show that we use the something called translation operator, so translation operator. So this is translation operator we will use. So ground state here are some ground state. Since ground state is translation invariant, so the Hamiltonian is J sample plus S J and then J plus 1. So that the ground state translation invariant, so the output is equal to ground state translation operator target. Sorry, target. So like this. So we assume T ground state is the same as ground state. So here is translation invariant. Then T dagger, you understand T is equal to T dagger exponential delta J, delta J, T. J is equal to S. T. Okay? And this is equal to and then exponential. So this means that this acts as this one in the J plus 1, right? J minus 1, sorry. J minus 1. J minus 1. So this means that and the theta J is just delta theta times J, which is 2 pi times NS. Okay, so this means that so this is minus alpha delta theta times over SJP, J equal to 0, 2, and S minus 1. Okay, that's what we have. Okay, and then this one itself is the exponential of constant okay, so this is equal to exponential minus I sum over G is equal to 1 to and S minus 1 and J Sj D. So since J equals to 0, J equals to 0 here, this is just a 0, right? Theta 0, theta is 0 is 0. So therefore you just multiply just by 1. And so you can start with J equals to 1 instead of J equals 0. And now, so this really looks like the U LSM, which is written here, which is not written here. So this is J, and this is equal to E to D minus I, theta L, S L, and F, and F, and S, D, and U LSM. Well, that's actually. Okay. Okay, so then now also we know that this guy is just E to D 2 pi I S L D, which is equal to minus 1 2 times S. Okay. So this is just another 2 times. Okay. So therefore, and we know that the ground state of times Lsm now is equal to minus 1 to 2S, and then U Lsm ground state U Lsm E to the minus, so this factor I delta stator sum over Sjt and J equal to 0 to S minus 1 acts on Lsm. And then this is in fact not Lsm ground. But this is in fact this is S only. And there's theorem telling that there's a SC fault ground state in C ground state. Here's this is theorem. So this is called Marshall Lee and Matthias theorem. Theorem telling that this is the case. So now you can show that this is equal to just minus 1 to 2S GS times Lsm. Okay. So therefore, so if the half integer, circular half integer, there in fact we have a negative sign here. So therefore, the intersection and the inner product needs to be 0. That's the case. Is it okay? So therefore, so this is the proof of the Lsm theorem. or maybe. Okay. Any questions for them? Fine. So now we'll move on to S equals 1. What's the AKLT? So Hamiltonian is given by something like this, and sum over J, spin, straight, and like this one. So this is a Hamiltonian rule of the and I from now on I will set J equal to 1, just J equal to 1. The one can show that this is equal to sum over J projected to Sj plus Sj plus 1 is equal to 2. Minus 2. So one can show like this. So this operator is called projection in spin 2. So note that each spin has S equal to 1. So therefore, if you take S equal to 1, S equal to 1 is three-dimensional space. I mean, spin 1 plus spin 1. If you take the tensor product, you can have the decomposition in 2 state plus spin 1 state plus spin 0 state. So that's the case. I mean, often people just write down that like this way. Okay. So this is spin 1 half, spin 1, spin 3 half, and then this spin 2, like this way. So number of box divided by 2 is a spin. Number of box divided by 2 is a spin. And if you take a tensor product, you can just join them together in a 4 stage, right? 4 box field. Or you can cancel. So you can cancel one box like this way. And if, so, how is that? Horizontal 2 boxes you ignore. And so therefore you get this. Or you can have this one. So the horizontal 2 boxes you can ignore. So you get that. So that corresponds spin 2, spin 1, spin 0. And you can just look at the dimension. So what is the dimension of spin 1 state? 3, right? So 3 cross 3, 3 cross 3 is equal to, what is the dimension of spin 2? 5, 3, 1. 9 is equal to 5 plus 3 plus 1, like this. Okay? And here you consider spin 1 state in the 2 side, the 2 adjacent side, and take a tensor product. And this projection operator, you just project to this one. You just project to this. That's what it is. 哎呀，你看。Eraser is West to somehow. I'm not sure it's meaningful to have eraser to be. German is like. Anyway. Okay. So now let's see why they're equal. So I'm going to derive this equality. To do that, we just consider the following thing. So this one can be decomposed like this way. And then, so this one is equal to, so Sj plus 1, Sj plus Sj plus 1. And here we know that this is spin 1 state. So therefore, S squared is equal to what? Is it okay? So in quantum mechanics, you learn that J squared upon J is equal to J plus 1. Right? Like this one. You learn this one. The same thing. So if spin J is equal to 1, it's just 2. This is 2. This is 2. Okay. And then, so this is equal to therefore, sorry, I'm confused. How do I show? Just hold on. Got confused. And then, what kind of value Sj cross Sj plus 1 can take? Sorry, just hold on. So this, so I mentioned this should be either 0 or if it is 1. If it is 1, what's going to happen? This is 2, and then if it is 2, what's going to happen? 2, this is equal to 2 times 3 is equal to 6. 2 times 3 is equal to 6, right? Okay. So therefore, okay. So then, so Sj dot Sj plus 1 is equal to minus 4 when Sj dot plus Sj plus 1 is equal to 0. Is it okay so far? And that this is equal to, it should be 2, so plus 2, Sj plus Sj plus 1 is equal to 1. And then here, 6, Sj plus Sj plus 1 is equal to. Is it okay? Is it okay? Do you agree with me? If it is 0, so 0 times 1 is 0, right? So therefore, 2 plus 2 minus 4 is equal to 0. If it is 1, so 1 times 2 is 2, right? 2 plus 2 minus 2 is equal to 2, right? Like this. If it is 2, 2 times 3 is 6. 2 plus 2 plus 3 is equal to 4. Now, like that one equation. AKLT, I'm done. Okay. So then Hamiltonian is equal to minus 4 plus 1/3 minus 4 squared is equal to what? This is minus 3 plus 16 over 3, right? Is it correct? Is it correct? So therefore, E is equal to 4 over 3. Is it correct? I'm not. Sorry, I think actually I'm doing something stupid. I think there must be 2 right here.
Yeah.
2 right? So therefore, I have to divide by 3. Is it correct?
Yeah.
Oh, sorry. So therefore, so this should be 2, and this should be 2. So this should be 6. This should be 4. Okay, so this is 2. So minus 3. If you notice that, please tell me. Okay, so next is minus 1. Minus 1 plus 1/3 is equal to minus 3/3. And then this is spin 1 in here. That's spin 1. That's spin 2. Is equal to 1. That's why it's 1. So 1 plus 1/3 is equal to 4 over 3. Okay. So therefore, this should be sorry. It should be. So if there is no, if it is spin 0 or spin 1, there is no such a term. So therefore, minus 2/3, which is minus 2/3. Okay. On the other hand, if it is spin 1, this term becomes just 1. So therefore, 2 minus 2/3 is equal to 4/3. Is it okay? Okay. So now I show that in.
有的话两个来挂了。
Okay. And also, this constant is not important. So therefore, instead from now on, so we consider AKLT is something like a sum over J into projection to simplest state. We consider like this. Now I don't care about this, the overall factor 2, and I don't care about this minus 2/3 and so on. So thank you. Yeah. So what is the ground state? So the ground state, we can just construct such a problem. Act on BBS. We want to construct such a state. We want to construct such. It's called BBS, means the balance on solid. So the construction is very intuitive. So each each field dot, small dot, you have a spin up, a spin down, 1/2 state. Okay. And then for this solid edge, the solid edge, we assign the following to the spin 0 state. Spin 0 state. So if you add this one, so now here is down, here is up. So it's a linear combination of time. If it is up, down, and down, up. And the linear combination. To make this edge is a spin 0. It's spin 0. Now, and we take the so the last state is performed. Is something like this on cross. J equals to 1 J and M. 1/2 root. And now you symmetrize here. Okay? If you can symmetrize here to make it this state. So here you just act as symmetrize operator. So here P hat J. So P hat J acts on so this is J operator. So here you have state sigma J left. So this is sigma J right. Okay. So you have a sigma J left, and then you have a sigma J right. It's the symmetrize of operation JL. So this is symmetry operator. But I think this is Q and the prime. Yes, so I think the notation is somewhat strange. I think I should write down like this. So this is the thing. So now since you symmetrize the operator, so around this form, so okay. Around this form, so you have a spin 1 operator. Spin 1. So if you symmetrize it plus minus, you have either this one or like this way, or like this one. So each form you have your assign spin 1 state, and you treat this state as the state that appear in the AKLT. And this by construction. If you look at that, so this is Sj plus 1, Sj plus 2, and so on. So this is Sj plus 3, Sj like this. I think my notation is somewhat strange. Prime Jr J. And each place you symmetrize. such a spin 1 half state to get the spin 1 to get the spin. Okay. So now by construction, so this becomes this EDS is in fact product of P at J, J is equal to 1 to NS, and then X is free bond state. Free bond state. And by construction, if you look at this, each adjacent side, so this is Sj, and Sj plus 1. And if you look at this adjacent side, we only need this state on spin 0 state. So in this edge, you only always have square root plus minus plus, like this way. So therefore, what's left is these two in 1 half, the most edgy. And 1 half state can only 1 half plus 1 half. And the product is again for this continuous. So spin 1 or spin 0. But most this state can create spin 1 or spin 0 because this guy already created a spin 0 state. So these two, leftmost spin and rightmost spin, can create at least spin 1 or spin 0. So therefore, it projected out from the AKLT component. Okay. Therefore, by construction, this is also mathematically satisfied by construction. Okay, so that's any question at this moment? So what we are doing is very like a very simple thing, but something very it leads to something very deep. Any question at this moment? Okay. From now on, what we are going to show is as follows. From now on, what we're going to show is that let's take a look at the property of this ground state here. First of all, there's some hidden. Okay. So I'm going to use this one. So I'm going to use this one. Suppose this is spin 1. Spin 1. Like a spin platform. Like a. So we can have, so spin 1 is that we can have 1, 0, 0. This is, let's see, 1. and then 0, 1, 0. So this is just 0. And the minus state is the 0, 0, 0. And suppose this is plus. So this means that suppose this is plus. This means this is plus and this is up and this is up. You get this is plus. This is 0 and this is 1. And since we so they form spin zero state. So therefore this spin must be spin down. You can have either plus here or minus here, and you can just symmetry. Okay, suppose this is plus. So this, if you symmetry, you get a 0. Okay? 0. And now, if you move on to here, you have to have a spin down. And then here you can have either a spin up or spin down. So you suppose you have a spin down, you have a minus. Okay? And since you have to be spin 0 here, so it has to be spin up. Okay? So you can have it spin either spin up or spin down. So let's suppose you have spin. And it's a plus. And you can continue the game. Like this way and so on. Next is something like this way, and then this way you get fine. And then if you write down the state, it's something like a plus 0 minus plus 0 minus 0 0 plus minus 0 0 0 minus plus 0 0. This kind of states will show. And if you remove 0, you always have plus minus plus minus plus minus plus minus plus. That is a hidden anti-paramagnetic order. As you remember, for high temperature chain, Hamiltonian is the plus sum over Fj dot Sj plus 1. I mean, numeric sides tend to be the opposite. You make the Hamiltonian negative. Hamiltonian like a lower. Energy low. And then so if you remove 0, you always have the, how to say, you can always see this target, plus minus target. This is because we join this spin 1 state by spin 0. Spin 0. So this, if this is up, it has to be negative. So therefore, if it is negative, it becomes negative minus, which means plus minus. But here, so you always have an opposite spin when you go to the next side. Okay? And if you choose that one, you can have either whatever, 0 or some either plus or minus, but it has to alternate once you remove 0. So that's hidden anti-paramagnetic. In addition, so often spin chain. If we call the open spin chain, is 4 degenerate ground state up here. So suppose you consider open spin chain. So if you open spin chain, so here you always have you always have like a spin 0 state. So therefore there's some correlation up here. But at the edge, you can have the plus or minus. So you can have plus or minus. Spin up or spin down. Here spin up or spin down. So this is so therefore here you have the G2 cross G2 degrees of freedom. Plus minus. So therefore open spin chain I'm going to it has the okay, maybe 4 degrees of freedom. Sure. Like this. Okay. And then from now on, so we need to show that here is a gap. Is a gap to ground state. Ground state. So the spectrum is something like this. So for close the periodic spin, close spin system, the energy spectrum is really like this. So now so this is grounded EPS, and external. Yeah. So this can be shown. So we are going to show this by showing that the explanation again. Okay. Of the correction function. In particular, we'll compute this BPM as J, and then as I don't remember J also L, BPS, and normalized by inner product. And this one is proportional to some number. One number in yeah. So we will show from now. So if it is the case, if it is exponential decay, so it's a strong reason to believe that it is the distance gap. Now the other thing we're going to do is to see something called French. Sorry. Yeah, so the sorry, I forgot. Yeah, story mode. For reference, which actually this is going to be homework actually, and it's going to be homework. So this way we define something, some operator as J, and then E, and the exponential E to U by R, sum over J is equal to K is equal to J plus 1 to E. L minus 1. Okay. Like this way, and there's J, no, FL. C, alpha PBS, and PBS. So now I call this one this is the final operator of this string. So if you consider such an operator, in fact, so this one is not this. It's not this. So it's not this. But if you consider that some sign of this trivial, so which is Sj squared. J equal to 1 to 1 to like if you consider such state, and if you consider ground state of all string, then the ground state. Here you can easily see. So what is the ground state of this trivial Hamiltonian? All zero. So all zero. So if you put the D1 and 0 and everything 0 right here in the middle. So therefore this will become 1 and 0. So therefore this should be 0. However, one can show that this is non-zero for this AKLT state. For ground state is non-zero. Therefore, this can be understood as the, as I mentioned, so if you consider HS is the F trivial Hamiltonian plus 1 minus S H AKLT, and then consider S to be here, S equals to 0 and 1. So there is some critical value, S critical. S critical. And here is the trivial phase, this is trivial phase. And this is called Harlem phase. And this string order parameter can distinguish these two phases. Because I mean here for trivial phase is supposed to be this expression value of this string order operator. Whereas here it's not the one. Okay. So to show both the property from here, it eliminates to construct so-called matrix product evaluation. so-called MP or BB. So the bound we are looking at the follows. So we want to is sum of sigma where the base of the A sigma 1 A sigma ns where sigma 1 of the sigma ns. And then this is either plus or minus, so spin up or spin down. Spin up and spin down. That's what we want. No, sorry, no, sorry. No, sorry. This one is plus sigma is plus 0 and minus. You can have a plus 0 and and the A is the 2 by 2 operator. So the schematically we just write that A is the 2 by 2 matrix. And this state can be understood as something like this one. It's a 2 by 2 matrix. Okay. So now, so we consider that each type you assign some 2 by 2 matrix A, which will map as follows. So A plus is always the what? Sorry, I just got confused. So here you have the A1, right? And then we're going to try to do it for sorry, so this should be 0, 0, 0. And the plus is always the sorry. So here, yeah. So this is plus 1. Yeah. So if you have a plus, so P1 is always like this thing. And if you go to here, you have to have a negative, right? Negative side, negative side. So therefore, so you have to, so if you have 1, 0, it should go to minus square root 2. It's to be like this root. Because I mean here you have the square root 2, plus minus, and the minus plus. spin up, spin down, spin down, spin up, like this way. And if you have here spin up here, you need to assign the minus square root, minus one over square root 2 here in down case. However, it's not like it. So you only have a spin up. So likewise, if you n minus, so you only have spin minus, spin down. So therefore, so if you go to here, it should be up, spin up, and then the factor is 1 over square root 2. So therefore, it should be square root 2 and 0. So this state is just marked that the spin up state goes to spin minus when you move to the next side. So that's what it is. So in this case, if you have a spin down state, acts on this n minus, you get a spin plus on the next state. That's what it is. Okay. Then at 0. So at 0 case is much more subtle. In 0 case, you can either have here now I got confused. Why shouldn't that happen? Why should I not? If you line up like this way, it should go to like this way. Sorry, I got confused. I think my explanation is not right. Sorry, I got confused. Why should sorry. Goes to sorry, I got confused. Okay. I think my understanding is not correct. I think so at the end of the day, so what I want is something like this one. And that is really corresponding to the BBS tape in the matrix product form. Matrix product form. But I don't know why this is happening. Sorry, now I think I think I understand what's going on. Now, so I think we should call this is one. This is called. So this is called one stage, and this is the two stage, likely. And then, so if you have, sorry, sorry about that. Nice. So if you have here plus and then minus, then this stage is so it's no longer plus sign, so it should be annihilated. On the other hand, so this is plus minus. Okay, so I think that's what it means. So this is one state here. And in one state, if you have plus sign here, you just move to the two state. So therefore, this is one state is moved to two states with up to sign, up to some factor. On the other hand, if you have the opposite, so if you have the opposite, this way is plus and this is pin down, this is two state. But then you can have, if you have a minus here, you just go to one state by this. And that is moved from two states to one state, like this. Do you understand why? Sorry. Okay. Okay, let me explain more easier. Sorry. Okay, I think that's okay. So now, so you can here in the balance part, you have sorry. And I call this one is the one stage. And this is called two stage. And two stage. And suppose you have one which one is that? I don't know which one is better. Maybe this is one stage like this way. And then if you can have plus sign, you can have like this way. So this part will become 1. On the other hand, it becomes 2. Therefore, matrix should be something like a 0, 0, 0. So if you act one state like this way, so one is like a 1, 0, and 2 is something like a 0, 1. So if you act on like this way, you get something and the plus. So therefore, 1 is not 2, 2. That's what I meant. On the other hand, sorry about that. So on the other hand, if you have the so here we have two states. In the two states, if you have a minus here, like this way and then this way, then it becomes one state. Therefore, A minus should be something. Because if you act in two state like this way, it becomes one solution. That's the one. It's just not correct. On the other hand, so this is minus k here. On the other hand, in here, if you have a spin zero part, so this is in zero part, then if you have like this way, it should be mapped to like this way. Okay? Because this, in the middle you have plus like this. So here you just I call it 2 is mapped to 2, or if you have yes, it's one state. If you have one state, it's mapped to 1, like this. So the output A should be diagonal. And if you are careful about all the sign and coefficients, this should be the correct normalization. This is the correct normalization. Sorry about it. Okay. And unfortunately, because of my explanation is really bad, I'm running out of time. So and if you just multiply them together like this way, and then just correlate this upper sigma to be being one state in here, and sum them up, you get a balance point state like this. So that's the matrix product form of BBL. And then yeah, time is up. I will explain why this is the VBS space, and from using this one can show that the equation function is exponential decay, and also singular parameter is the equation value is from D. That's the plan of the next lecture. Okay, sorry about that. Last part. Okay, let's stop here, and if you have a question, please let me know. Yes. So one thing that I wanted to mention is that the grade is determined by 50% of homework, 5% of homework, plus 50% of final exam. And this is, I think this is, the final exam is this thing, if I'm not wrong. Please correct me if I'm wrong. And it's a cutting. So you can bring book and so on, but you cannot bring laptop. But I allow you to bring notepad, iPad is okay. But the internet should be switched off. So, and you cannot type. So it can be used as a reading, only for reading. So iPad or no iPad or some tablet, it's not laptop. You cannot type on. So laptop is not allowed. But iPad is okay. Like iPad, like this kind of device is okay. But internet is switched off, and then you cannot use even like how to say iPad pen. You cannot use iPad pen. It just can be used only for reading. So you can download whatever PDF to see that. I mean, I don't like some people just print like 100 pages, like 200 pages, whatever. Not. I mean, it's just waste of. Waste of paper. So that's why I allow this one. I mean, just a huge amount of whatever. To print out and bring to the final exam. So that's the case. So not all students are here. So you should tell your colleague, laptop, even if you bring a laptop, you cannot use it. But if you bring like this one, you can use it with some conditions. So that's that. And if you have any question about the finite curve, just let me know. I think that's what I want to do. I think that's what I want to do. Yeah. And then it's recorded, so please tell your whatever colleague, about this rule.